Hello, everybody. I'm Robert Burklund. I'm a graduate student at MIT, and today I'll be telling you a little bit about my research. So my research has a lot of different things I do, and they're all kind of unified by the themes of homotopical thinking and really thinking about stuff like that. And so the project I'll be telling about today is a new way of constructing the end self maps and something cool you can do with it. And so we're diving into things. Maybe give you a remind you on the end self maps. And so definitely Hopkins and Smith said that they proved that finite spectra, if you think about them up to six subcategories, they're classified by a single number type. So finite spectra are classified up to six subcategory by type. And so this means that to each x we can associate a number n that is its type. And so then they go on to show that these x are picked out by having certain non-nilpotent periodic self-maps. So on x of type n, we have a self-map Vn capital N, which goes from suspension to t to the n minus 2 n of x back to x. And this guy is, for n capital N very large. And this guy is non-nilpotent. And lifts the n to the n on Rabi K theory of x. Okay. And so this is all great. We have finite spectra. They're only non-nilpotent self-maps are these Vn self-maps, and you know which one you're supposed to see based on the type. But there's this n here, and n has to be very large. So this raises a question: if I allow myself to tune which type n spectra I'm looking at, how much control over n can I exert? So the question is, how small can n made? And the theorem I'd like to tell you about today is close to a complete resolution of this. And so for each height and prime, there's going to exist a finite type n spectrum x, such that if you look at its telescopic localization, it has at the end of the first self-map. And now that is not quite the same as saying that there's a finite spectrum with at the end of the first self-map. What it actually allows you to say is that the GCD of the n such that you have a self-map of that form is 1. So like an example of something that might happen is that you might have a spectrum that admits a Vn to the n self-map when n is 2, 3, 4, and so on. It just doesn't admit a Vn to the first self-map. But when you localize it as to invert any of these natural numbers, that difference disappears. And I think that removing this last condition, removing this GCD condition, things become substantially harder. And it's not necessarily, doesn't need to be true. At least I don't have a reason to strongly believe. But now let's get into discussing how one would go about proving this theorem. And for this, let's kind of go back a step and look at how do we typically produce the n self-maps. So the standard way, that comes to us from the original proof that these things exist by Hopkins and Smith, is that you look at the Vn self-maps and you look at classes that would correspond to them in an atom spectrum sequence, and you then show that okay, there might be a differential off of this Vn class I see, but then on some Keith power the differential gets longer and longer, and eventually it has to survive because the differential is just too long, and vanishing lines and such things force it to exist. That's the typical argument. And so by working with Strugowski's category synthetic spectra, we improve this. The way we improve this is that the idea is that the atom spectral sequence when we formulate in terms of synthetic spectra, goes to the covariant, or not the covariant of tau, but the tau box. And for our purposes here, this leads to a substantial improvement, which is, if we think about the map cofiber tau to the end, receiving map from cofiber tau to the end, this map is a square zero extension. And so what this is telling us is, let's say you're on the E5 of the page of the atom spectral sequence. Typically, you would think of the D5 differentials on the E5 page, and then you go to the E6 page, and that's that. But this square zeroness is saying that really, things don't start to really get crazy until you get to the E9 page, if you really know what's going on the E5 page. That sort of, that from the E5 to the E9 page, it's a square zero extension. And so what this allows us to do is to kind of boost the methods that Hopkins and Smith built, so that instead of going one page at a time, you essentially double -1 the page you're on every time. And this allows you to produce these maps much more quickly. And in situations where their techniques wouldn't be applicable, they're now applicable. And so you might think of this as a sort of a topological version of the Cousteau transgression. And insofar as this, this synthetic viewpoint on spectral sequences can be applied to any spectral sequence, the same lemma will apply in that situation. All right, and at this point you might be wondering, well, sure, it's nice to be able to produce, better powers of things, but this method can't possibly be applicable to producing the end of the first, because you need your thing to have better permanent cycle from the outset. And the thing here is that this lemma gets used in a very roundabout way. And so the actual approach that I take to constructing things is the following. It's what we want to do is we want to build a non-finite spectrum that does have a V-end first self-map, and then prove that it is compact after telescopic localization. And then after that, you lift it back to produce a different finite spectrum. And so the way you want to think about this non-finite spectrum I'm trying to build is that it's supposed to be a compact, like finite thing that's at height n, and then an infinite amount of junk that's acyclic at height n. And so it's it's got a core piece we care about, and a huge amount of infinite junk that arises because of the construction. But when we localize, all that goes away, and it's sort of we just have a nice small object. And so the thing, what we to build this thing, what we do is we consider y of n. This is the Mahler-Diagonal-Schick spectrum, y of n. And we think about the action of the E2 center on this guy, right? So y of n is an E1 ring, and we have its E2 center, and that acts on it. And using this, we can construct our x. And so the idea is that, y of n does have a v into the first self-map. And so as long as we can manipulate y of n in order to not break its v-n self-map, while at the same time turning it into something that's telescopically compact, then we would. So that's what we do. All right, well, thank you for your time. I look forward to seeing you guys in the actual event.